We're going to attempt to improve on the method of using rectangles to estimate the area under the graph of a function. On this slide for now, I just want you to look at the diagram here that shows a continuous and smooth curve, the graph of a function, and there's an A and a B on the X number line, and above on the graph I've marked and divided the interval into 4 subintervals. So altogether there's 5 points, 1 at the beginning at A, 3 in the middle, and then 1 at the end, but there's 4 subintervals altogether. And the shape we're going to draw this time is a trapezoid by just joining consecutive points on the graph of the function. And you can see that for short distances, the top edge of the trapezoid really does go along with the shape of the graph really well. Maybe a little bit better when the curve is not bent as much, but even on these first and last 2 intervals, there's really not a lot of empty space that we haven't really accounted for. And so you can see this is going to be quite a bit of an improvement over just drawing 4 rectangles, left side or right side or midpoints. Either way, this is better than any of those. So what we need to do first is kind of do a little geometry review. How do you find the area of a trapezoid when it's drawn like this? So let's just go back to this one drawing here that's got a trapezoid drawn about the same way they will be drawn for our calculus problem, and that is the parallel sides are vertical, and then the width or the distance between the parallels is the span across the bottom, which is like what we're going to have on the x-axis. The rule you learn in geometry class, at least the way I remember it, it would be the way you think of it here is the area is to take the average of the 2 verticals. So I would take 3, and on this one I would take 3 and 5 divided by 2, and then we're going to multiply by the width of the base, which is 2. And so my calculation is 8 divided by 2 times the width 2, and so my final answer to this is going to be 8. So again, if you want to write it in words, I could think of it as the average height multiplied by the width will always give you the area of the trapezoid when the heights are the vertical and parallel sides of the trapezoid, and then the width is straight across the bottom like this. So think average height times width. So now let's just translate that back to the graph and to show how we might add up the 4 trapezoids if there were 4 or more. Now to name some additional parts here, I'm going to name these numbers on the x-axis x sub 0, and then we're going to count by 1s, and so that my last one will be numbered 4, corresponding to the number of trapezoids. So my initial starting point will be called x0, and then if I tick mark off here, I will end at x sub 4. And now we'd like to write out how I would add up the 4 trapezoids. We will try by marking off then and calling each of these widths delta x. Now they may or may not be the same width, so I'm going to number those 2. I'm going to call that one delta x1, and then delta x2, and this is delta x3, and this one's delta x4. Now sometimes we'll have all 4 of those widths be the same, and they look the same in this picture, but they may not end up being the same. It just depends on what information you're given. So let's write out the 4 trapezoids. Remember that the rule for area is to take the average height and then multiply by the width. So what I'm going to do is I'm just going to number these trapezoids. Number 1, number 2, number 3, number 4, and as I write them out here, we'll identify them by trapezoid 1, 2, 3, 4. So the area of number 1 would be the average height of it, which is the function value at both x0 and x1. So I'm going to be adding f of x0 f of x1 divided by 2, and that will be multiplied by the width of that trapezoid, delta x1. And we just work our way across. So in the second trapezoid, the heights are measured at x1 and x2. So f of x1 plus f of x2 divided by 2 to take the average, and we're going to multiply it by the width of that trapezoid, delta x2. And we have 2 more to go, so I'm just going to keep writing out in the same way. The third trapezoid, the heights are measured at x2 and x3. So we're going to average those. Times the width of the third trapezoid. And then we will take the fourth trapezoid, which is measured height at f of x3 and f of x4. So average those, and then we're going to multiply by the width of that trapezoid, delta x4. So when I write it out this way, you really can't see the trapezoid area formula is just being used 4 times. If there were more trapezoids, you'd have to do more of those, but that's basically what you're seeing here. The average height of the trapezoid each time times the width. So we're going to try this out on an example where all the numerical values of the function are given. All we really have to do is lay out and evaluate the trapezoid, what we call a trapezoidal sum. Now what I'm going to do, in fact, is make a very simple sketch of what information I'm given here. So there's a function that we're going to draw on the interval 0 to 6. Here's 6. Now notice here the x values that were given were 1, 3, 5, and 6. So f of 2 and f of 4 are missing. Now I'm going to mark in green here where the function values are. F of 0 is 1. Actually, I better mark off the x-axis, y-axis here up to at least 7. 2, 3, 4, 5, 6, 7. Maybe I'll go to 8. And so now in green here, f of 0 was 1. F of 1 was 3. F of 3 was 4. F of 5 was 7. 4, 5, 6, 7. And then f of 6 was back to 5. 1, 2, 3, 4, 5. So it is right about there. Now, if you wanted, you could actually draw in a curve. You presume it's a smooth curve, perhaps. So maybe the graph looks something like this. But now in yellow, let's actually draw out the trapezoids that will be represented and we'll try and use to estimate the area under here. So by marking off the first 2 points, connecting them with a straight line, you now have trapezoid number 1 right there. And if I just join 2 consecutive points with a straight line, keep going, here's trapezoid number 2, and then I'm going to connect with a straight line again. Here's number 3. And I'm going to connect with a straight line again. And here's number 4. All we need now is to know the area of a trapezoid is the average height multiplied by the width. Notice this time the widths are not uniform. The first interval goes 0 to 1, and so the delta x is 1 unit. In the second subinterval, the width is 2. In the third interval, the width is also 2, and then on that fourth interval you're back to being 1. Okay, so this is like delta x1, delta x2, delta x3, and delta x4. Now we'll just approximately measure this integral, or the area underneath f of x. And remember, it's an approximation. It's not really the value, it's the approximate value. So we'll take just one trapezoid at a time. The first trapezoid is going to be f of 0 plus f of 1. And I'm going to just write in the values from the table this time. So I know that f of 0 is 1 and f of 1 is 3. So I'm going to take the average of those and multiply it by the width, which is 1. In the second one, the two heights are f of 1 and f of 3. So I'm going to be adding 3 plus 4, averaging those, and this time the width of that second trapezoid is 2. And I'm on trapezoid number 3 now. The heights are f of 3 and f of 5, so I'm going to be averaging 4 plus 7 and multiplying by the width 2. And for the fourth one, the heights are f of 5 and f of 6, so I'm going to be averaging 7 plus 5 and multiplying by the width 1. I'll do one last little bit of simplifying, then I'm going to leave the final calculation for you to work out. The average height here is 1 plus 3, which is 4. 4 divided by 2 is 2, so this is going to be 2 times 1. Here I have 3 plus 4 is 7 divided by 2, so this is going to be 3.5 times 2. Here I have 4 plus 7, which is 11, so divided by 2 is 5.5. This is going to be 5.5 times 2. The last one is 7 plus 5, which is 12, and 12 divided by 2 is 6, so this is going to be 6 times 1. And I'm going to leave it for you to add up the values to get the final numerical value of the approximation. It would just be to add up the 4 quantities that you're going to get here. The other one we'll try is where I give you an exact definite integral, so this time we know the function, but we don't have a table for it, written out for it, or have any of the details. But it does say how many trapezoids to use when it says use n equals 4. So if I read the definite integral, it says we're going to take across the interval 1 to 3, and the function is the natural log, or the square root of the natural log of x. And so this time what I'm mainly going to be drawing as a graph is a layout of the x-axis. And so this is supposed to take us from x equals 1 to x equals 3, but dividing it into 4 parts, meaning I'm going to go and count by halves. So I'm going to go from 1 to 1.5, 1.5, to 2, and then to 2.5, and then to 3. So the function is going to be a positive valued function. It's going to be it's going to be up here. I'm just going to assume it's going to roughly be about like a regular square root function. And so there will be now a series of points that I can mark on it every half a unit. Now let's take green now to lay out the trapezoids. By connecting every 2 points with a straight line, and then sorry, I'm going to miss my mark a little bit here, but there's going to be 4 trapezoids again. And so all I really need to do is measure the function value, f of x equals the square root of the natural log of x at each of these 5 spots. Okay. And this time what is uniform is the delta x. Every delta x is going to be a half every time. So all we have to do now is go along and use the area of a trapezoid method and find the areas of the 4 trapezoids. And so we could make a table if we would like, or I can just translate using the name of the function what I'm going to be doing, and then I'm going to be doing most of the calculation on the calculator. So we want to evaluate the integral 1 to 3 of the square root of the natural log of x. Remember, it's an approximation. So as I look at the 4 trapezoids, the very first one is going to be measured the heights at 1 and 1.5. Now, I could write this out here in the form of the function here. The square root of the natural log of 1, the square root of the natural log of 1.5 divided by 2, and then the delta x is 0.5. For trapezoid number 2, the heights are measured at 1.5 and 2, so it's going to be the square root natural log 1.5, square root natural log of 2, divided by 2, times the width, 0.5. And we'll just have the last two to do now. The square root of the natural log 2, square root natural log 2.5. So we're taking the average of those times 0.5. And then the final one is from 2.5 to 3. So the natural log of 2.5 plus the natural log of 3 divided by 2 times 0.5. The rest of this you will have to do with your calculator, or you could find the values of each of these if you were just to enter the function into your graphing calculator as y1, and then just get your calculator to make a table that has every output starting at x equals 1 and counting by 0.5s until you get to 3. You could just read those numbers off of the table and use them to do the calculation.